All right, so today we're going to continue on talking about the periodic table. And we're going to talk specifically about the element families and the groups that have specific names. So let's get into it. All right. So the element families, I'm going to move myself over here this time. Okay. So the element families have similar properties. All right. The families of elements consists of such important common elements that the families are given specific names. So we have groupings of elements that are so common and used so often that we give them specific names. All right. So we're going to talk about each of these. Now, hydrogen doesn't really have a family name because it doesn't really have a family. Yes, it is in group 1, but hydrogen is not really part of group 1. Hydrogen, you'll actually see this in some periodic tables, hydrogen is actually up and separated from the rest of the periodic table because it's kind of its own little thing. Hydrogen's special. It has only one valence electron. Its reactivity is that hydrogen is highly reactive and forms either positive ions, cations, with a charge of +1, or it can sometimes form negative ions, anions, with a charge of -1. So you either have a 1 plus or a 1 minus on your valence charge. So 1 plus means it lost its electron, it gave its electron away and became positive. And that's what hydrogen does most of the time, but sometimes it will actually gain an extra electron and become a negative, right? Hydrogen is kind of the orphan, doesn't really have a family, it's kind of its own thing, okay? So moving on, group 1, excluding hydrogen. So all the rest of group 1, lithium, sodium, potassium, cesium, rubidium, as you move down, okay? They are called the alkali metals, right? The valence, all alkali metals have one valence electron. They are in group 1. They have one valence electron, right? They are highly reactive. They react very easily. You won't find them in nature as an element very often. All right, very unlikely to find it as an element. It's almost always going to be in a compound because they are very reactive. They form positive ions. They only form cations with a charge of +1. All right, something you'll need to know that metals only form positive ions. All right, so that'll be important later on for you to know that. All right, so that's the alkali metals are group 1. Group 2 are called the alkaline earth metals. They are similar, but not quite the same. They're not the same family. They are similar. So if you remember that picture of me and my brother, we were the same family, but then our cousins are similar, but we're not quite the same. So alkaline earth metals and alkali metals could be considered cousins. All right. So you got the valence of all alkaline earth metals. They have 2 valence electrons because, again, they are in group 2. So they have 2 valence electrons. They're also highly reactive and form positive ions or cations with a charge of +2. Notice a trend here. Group 2, 2 valence electrons, +2. That's going to become important. All right. Groups 3 through 12, the transition elements, are also called the transition metals, okay? Because they are all transition elements and they are all metals, so they're the transition metals. They have various valences, all right? Groups 3 through 7 all have different valences, 3, 4, 5, 6, 7. And then actually when you get to groups 8, 9, and 10, groups 8, 9, and 10 all have 8 valence electrons for our purposes. And then 11 and 12 are 1 and 2. So they're all different. But many of these metals also have the ability to kind of act like they have different valences. They have more than one possible valence number. That's going to be explained later. So we'll get into that when we need to. They're not as highly reactive, and some have very low reactivity. In fact, things like gold don't corrode, they don't oxidize, they don't react all that well. Some are very low reactivity. They do form compounds, but not all that much. But they all form cations of various charges. So you could have some with +6, some with +2, some with +1, but all metals form cations, which are, again, positive ions. Groups 13 through 16, otherwise known as most of the P block, represent a change from metal to nonmetal, and therefore they don't have exact defined properties. You can kind of think about these as like blended families. You've got the one family, and then the mom's kids and the dad's kids, and so they're step siblings. They're in the same family, but they're not quite the same because some of them are metals and some of them are nonmetals and some of them are metalloids. So there's the change from metal to nonmetal. They don't have the exact defined properties. So these family names, each group is named after the element at the top of the group. So group 13 is the boron group because boron is at the top of group 13. Group 14 is the carbon group. And then you have the nitrogen group and the oxygen group. Some of them actually do have other names like the chalcogens and stuff, but I never even heard any of those names when I was learning chemistry in college as a chemistry major. I never heard all those names. I saw them in a book once. I was like, oh, so they're not really even used hardly anymore. So you've got the boron group, the carbon group, the nitrogen group, and the oxygen group. Okay. Each group's valence is determined by its column number. Okay. Their reactivity varies greatly. Each group consists of some that form negative ions and some that form positive ions. Again, nonmetals are going to form negative ions. Metals are going to form positive ions. Metalloids can do both. So they have various positive or negative ions depending on whether it's a metal or a nonmetal. So those are those element families. Group 17, it has a special name. Group 17 are called the halogens or halogens. I will most likely always call them the halogens. I've heard some people call them halogens. It's all a matter of emphasis on your syllables. Potato, potato, who knows? The family name of the halogens, group 17. The valence, all halogens have 7 valence electrons. 7 valence electrons. Their reactivity, halogens are highly reactive nonmetals, and they form negative ions or anions with a charge of -1. In fact, the best thing if you want to know which elements are going to react best with something else, you look at ones that have exact opposite charges, and that's what's going to react best. So the alkali metals are +1. They react very well with the halogens of -1. So one of the most common alkali metal halogen compounds that you are familiar with is sodium chloride. Sodium is an alkaline metal. Chlorine is a halogen, and they react greatly together to make sodium chloride, otherwise known as table salt. Group 18. These are some special ones. They are called the noble gases, right? They have 8 valence electrons, except for helium, which only has 2 valence electrons. And they do not react. They are chemically stable. They do not react with other elements. That's actually why they're called the noble gases. In fact, sometimes some places you hear them called the inert gases, but they were originally called the noble gases because back in the 1800s, 1700s, early 1900s, and even some places now, you have the noble families. So the nobility, if you were a noble person, the one thing you would never do is associate with the common people. So they were called the noble gases because they don't interact with the other elements. In fact, at the time Mendeleev created his periodic table, they didn't know about the noble gases. They didn't really know that they existed because they didn't find them in compounds because they don't form compounds. When they discovered noble gases, they added the 8th to the law of octaves. Before they only had, it was every 7 elements, and then the 8th element was the repeat. But then they found the noble gases. They added a whole column to the periodic table of the noble gases, and that completed the octave of 8. And now we had these ones that, oh, well, these are stable. And once they become stable, they don't react with anything else. And then you repeat the pattern. So you go from highly reactive, unstable, blah, 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 and then you get to stable, and then you go back to the other one for the next row on your periodic table. All right. So your F block elements, these elements are technically all belong between groups 3 and 4, right? We call them the inner transition metals. Again, they're the inner transition elements, and they're all metals, so they're the inner transition metals. Characteristics similar to those of transition metals, meaning they have various valences and transition-like properties, right? The two rows of the inner transition metals are named for the element that is at the start, lanthanum and actinum, or actinium, depending on how you want to pronounce it. So the top row, lanthanum is the beginning, so we call it the lanthanide series, or the lanthanides. And the bottom row has actinium at the head, so that's called the actinide series. So the lanthanides and the actinides. All right, this is going to conclude our discussion of history and organization of the periodic table. Next session notes, we're going to talk about trends in the properties of atoms found on the periodic table. And so how the elements actually change as you move from side to side. So that's that. All right.